In this video, we're going to discuss how to find the slope of a parametric curve. And just to give a little bit of a spoiler, for the slope of a parametric curve, we're still looking for dy over dx. So if you remember before from just calculus, if we have any old function, and we're interested in finding, say, the slope along a single point of that function, or finding something like a tangent line, well, slope is always equal to a change in y over change in x, a rise over run. And in calculus, we found out a very rigorous way to do this for continuous and differentiable functions, where we're able to take the derivative of a function with respect to x, and that would give us the slope. Well, in this case, we're still going to do the same thing for parametric curves. Except parametric curves, we know that both the x and y coordinate are functions of that parameter. Here we'll say that parameter is t. So we have some parametric curve defined by the functions x of t and y of t. And well, I'm just going to give away the slope. We're still looking for, like I said, a change in y with respect to x, except if we went ahead and tried to do this the same way, it's very evident that, well, our y function actually is a function of t, not of x. Well, we'll get into where this following slope formula comes from for parametric curves. As a clue, we're going to use chain rule to derive it. But the big spoiler from this video, if we're looking for the slope dy dx, if we're given a parametric curve, it's actually the ratio of dy dt all over dx dt. So it still looks like a change in y over change in x. In fact, it looks like a change in y with respect to t over a change in x with respect to t. Hopefully that gives you a little intuition. And this is the formula for finding the slope at any point along a parametric curve. Let's see where this actually comes from. And to make this a little more apparent, we're going to start off with functions that are nested within each other. And we're going to do an example on the right-hand side. So for example, say we have that y is equal to 1 plus x cubed, all raised to the 17 power. Let's clean up that y a little bit. So right now it looks like y is strictly a function of x, except I'm coming across and then saying, you know what? X is actually equal to sine of t. And let's make this a little more interesting. Let's go sine of, let's just say 5t. So if we're actually writing this function, well, y looks like a function of x who's inherently a function of t. So if we wrote all of that out, that would look like 1 plus what was previously our x cubed, which we know x is actually sine of 5t, so we'll plug in that sine of 5t. And that whole thing being raised then to the 17th power. So, okay, so we've just gone over, okay, we have nested functions, so what? Well, this on the left-hand side now is this looks really just like y is a function of t. So let's take that derivative. So if we look at dy dt, well, what this looks like, we have to do the power rule, so that 17 comes down. We get then this is 1 plus, well, what's there, sine of 5t, that quantity cubed, to the 16th power. And then by chain rule, we have to start differentiating inside. So taking the derivative of what's inside, we get 1 plus that derivative of sine of 5t cubed, which is 3 times sine of 5t, all raised to the second power. And then finally, the derivative of what's inside. And well, that's going to give us a 5 cosine of 5t. So this is a big chain rule type process. Hopefully we can all agree. And what do we notice about the right-hand side? Well, that right-hand side, that's actually a function of t. So what I mean by example, let's deconstruct this a little bit. So remember we had that y originally was a function of x, who's inherently a function of t. Again, that's coming from our realization here. So if we wanted to do chain rule here, and we're looking for dy dt, chain rule says keep differentiating from the outside in, and we keep differentiating with respect to the variable that's next. So in this case, we differentiate y with respect to x. And then, well, once we're now on the x variable, we have to multiply by the derivative of x with respect to t. Okay. So this is exactly the chain rule. And if we look at what we did down below, we first differentiated with respect to x. Well, let's take a look at that. So, remember our y of x function. dy dx from above. Well, just differentiating that gives us 17 times the quantity 1 plus sine of 5t, that whole thing cubed, to the 16th power. Oops. Got a little ahead of myself. This is 1 plus x cubed to the 16th power. And then, of course, times the derivative of what's inside, that's 3x squared. If we look at what dx dt is, that is that term, x equals sine of 5t. So differentiating that, this is where we get that 5 cosine of 5t. So if we look at the derivatives up top, well, that's that 5 cosine of 5t, that's the last term here. And well, what's in red is actually that first term and the second term from chain rule. It's just that we substitute what x was, where x we know is sine of 5t, but otherwise these statements are exactly equivalent. So when we actually did all this in these nested functions and then did the chain rule, it's the same thing as this more theoretical chain rule on the right-hand side. So hopefully this was a nice refresher in chain rule. And why should we care about that? Well, from that chain rule line, dy dt equals dy dx times dx dt, that's going to give us how to find the slope of a parametric curve. So let's take that idea to the next page. So remember, what we just saw was dy dt is equal to dy dx, which is what we care to find, times dx dt. Again, that's coming strictly from doing that chain rule type manipulation on the previous page. And well, if we care about the slope dy dx, we can just go ahead and solve for it. And we get that dy dx is equal to dy dt all over dx dt. And that is our slope of a parametric curve. So let's do a quick example of this. So if we're given a parametric curve, say x is equal to t squared plus 3t, and say y is equal to sine squared of 3t. If we want to calculate the slope along that parametric curve, well, we just have to take the derivatives of dy dt and dx dt and take their ratio. So dx dt is equal to 2t plus 3. dy dt, we get to do the chain rule. Sine squared of 3t, when we take the derivative, that 2 comes down. We still have that sine of 3t there, but then we differentiate the sine of 3t itself. So we get cosine of 3t, and then times a factor of 3. So we can combine that 2 and the 3 to equal 6. Okay. So if we finally get the slope, we just take their ratio. dx dt, well, that's just going to be equal to what we found for dy dt, which was 6 sine of 3t, cosine of 3t, and we divide it by the derivative for dx, or the derivative for x, dx dt, which we found to be 2t plus 3. And that gives us the slope along any point of that curve. And I want us to recognize something from this. This dy dt, that really is telling us, hey, we're looking at the slope. We're looking at a change in y over change in x, a rise over run. This right-hand side, though, even though this is a derivative, dy with respect to x, this right-hand side, it's entirely a function of the parameter t. So if I tell you, hey, figure out the slope at a point on the curve, we have to try and figure out, well, what t value or what value of the parameter do we plug into that slope? Sometimes it might you just come out and say, hey, figure out the slope when t equals 3, or you might have to figure out what t value to put in based on other information in the problem, such as we'll do a couple examples of that when we start calculating tangent lines to a curve.